All right, let's dive into a classic coding puzzle. Now, this one looks pretty simple on the surface, but trust me, its solution is so elegant, it's going to make you completely rethink what's possible with a tool you think you already know inside and out: binary search.
So, here's the deal. Imagine you've got this sea of numbers, all neatly paired up, except for one. One of them is all lone, and your job is to find it. But here's the real kicker, the thing that makes this tricky. You have to do it in O of log n time. Yeah, that one little rule is what turns this from a simple task into a really fascinating problem.
Okay, so first things first, let's get crystal clear on the rules of the game. They're super specific, and you'll see why in a second. They actually hold all the clues we need to crack this thing. This is basically the problem statement you'd see on a site like LeetCode. You're given a sorted array of numbers, simple enough. Every single number shows up exactly twice, except for one. Just one. And our mission, should we choose to accept it, is to find that one lone wolf element. Let's make this real with a couple of examples. Look at this first array. You can probably spot it, right? The number 2 is the odd one out. And in the second one, yep, it's 10. It's super easy for us to just scan it with our eyes. But the real question is, how does a computer find it efficiently? Now, your first instinct is probably to just, loop through the whole thing. And hey, that's a totally logical way to start thinking about it. But for this specific puzzle, that's just not going to cut it. It's not fast enough. That O log n constraint is the big, scary monster we have to defeat here. So think about it for a second. How would you do it? Maybe you'd compare each number to the one next to it, or maybe you're thinking of some clever math trick. Well, let's take a look at why the most obvious approaches, while good, just aren't fast enough for this job. And this chart just lays it all out, doesn't it? A simple linear scan, or even that classic clever XOR trick. They both work, but they both take O of n time. And the problem statement flat out says, nope, not allowed. It demands O of log n. Now, when you see a sorted array and an O of log n requirement, that should set off alarm bells in your head that are just screaming one thing: binary search. Okay, so binary search. But how? We're not looking for a specific value, right? We're looking for something different. The secret, the real key to unlocking this whole thing, is a hidden pattern. It's all about the elements' positions, their indices. Get ready, because this is the big aha moment. Okay, let's imagine a perfect array for a minute. No single element, just pairs. Take a look. See the pattern? The first one is at index 0. The first 2 is at index 2. The first 3 is at index 4. Every single pair starts on an even index. This is our baseline, our ground truth. This is how things should be. But look what happens the second we drop that single element in. It's like a glitch in the matrix, seriously. Everything before our lonely number 2 still follows the rule. The ones start at index 0, which is even, perfect. But look at everything after it. Suddenly the 3s start at index 3, an odd index, and the 4s start at 5. The whole pattern gets thrown off. And that is the light bulb moment. Our goal isn't to find the value 2. Our goal is to find the breakpoint. We need to find the exact spot where this beautiful even-odd index pattern shatters, because that breakpoint, that is where our single element has to be. So we've got our question now, right? At any given point in the array, is the pattern intact or is it broken? This simple true-false question is all we need. It lets us weaponize binary search to zero in on that exact tipping point, and we can do it lightning fast. Okay, here's the game plan. It's pretty straightforward. We're going to find the middle of our search space. But here's a little trick. We'll always make sure we're looking at an even index, the start of a potential pair. Then we ask one dead simple question. Does the number here match its buddy to the right? If the answer is yes, the pattern is good, everything's normal, so the lone element must be somewhere to the right. If the answer is no, whoa, the pattern is broken right here. The element is either here or somewhere to the left. All right, let's walk through this step by step. We start with the whole array, index 0 to 8. The middle index is 4. So we look at the number at index 4. It's a 3. Does it match its neighbor at index 5? Nope, 3 does not equal 4. That means the pattern is broken right here. So we know our answer has to be in the left half. We can completely ignore everything to the right. So we just move our right boundary down to 4. Boom, half the problem is gone. Okay, next iteration, our world is now just from index 0 to 4. The new middle is index 2. Let's ask the question again.
Does the number at index 2, which is a 2, match its neighbor at index 3? Nope, 2 is not 3. The pattern is broken again. The problem must be in this new, smaller left half. So we shrink our space again, moving the right boundary down to 2. All right, final step. Our search space is tiny now, just indices 0 to 2. The middle would be 1, but remember our rule? We always check from an even index. So we'll look at index 0. Does the number at index 0 match the number at index 1? Yes, 1 equals 1. The pattern is perfectly intact here. So what does that tell us? It tells us the problem isn't here. It must be to the right of this pair. So we move our left pointer up to 2. And we're done. Just like that, our left and right pointers are both pointing at the same spot, index 2. The loop terminates, we have our answer. The number at index 2 is, well, it's 2. We found our single element. And think about it. For an array with 9 numbers, it only took us 3 checks. That, my friends, is the incredible power of O log n. Okay, that was awesome. But you want to see something even cooler? For all you pros out there, that whole logic of make sure mid is even, then check mid plus 1, we can actually squash that down into one single absolutely beautiful line of code using a little bit of bit manipulation magic. So here's how this little piece of wizardry works. When you XOR any number with 1, all it does is flip the very last bit. Think about it. If you have an even number, like 4, its last bit is 0. Flip it, you get 5. That's mid plus 1. If you have an odd number, like 5, its last bit is 1. Flip it, you get 4. That's mid minus 1. So mid XOR 1 will always give you the index of mid's partner in a pair, no matter if mid is even or odd. It completely replaces that clunky if-else check. It's just so elegant. So what's the ultimate takeaway from all this? I mean, it's about way more than just this one little puzzle, right? This is about a fundamental shift in thinking, a way of approaching problems that top engineers use all the time. So here are the big ideas to stick in your brain. First, if you're in an interview and you see a sorted array and they say O of log n, your mind should immediately just go beep, 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 binary search. But second, and this is the really big one, binary search isn't just for finding values. It's a tool for finding any kind of transition point, the place where yes turns into no, or in our case, where pattern is intact flips to pattern is broken. So your job is to always be on the hunt for those hidden patterns. You know, being able to master this kind of creative, non-obvious use of a fundamental algorithm, that's what we call algorithmic maturity. It's when you stop just thinking about the textbook definitions and you start seeing these tools as a way to solve really complex problems in the absolute most efficient way possible. And you know, this fantastic quote from the legend himself, Edsger Dijkstra, just hits the nail on the head. Simplicity is prerequisite for reliability. Our final solution, especially with that little XOR trick, is just so simple. And because it's built on such a clear, simple pattern, it's rock solid reliable. That right there is what beautiful code is all about. So I'm going to leave you with a question to chew on. We just used binary search to find a break in an index pattern. So what other hidden patterns could you search for? Think about it. What about finding the peak in a mountain-shaped array? Or finding an element in a rotated sorted array? Or even finding the exact version of your code where a bug was first introduced? Once you start thinking about binary search as a tool for finding the breakpoint, the possibilities, they're just endless.